Venkatesan sir, now we have started streaming. You may start the meeting.
Okay, thank you, Yogarajan, Professor Yogarajan. Dear friends, welcome all of you. This is the second week of our meeting, and this is the first week of our formal lectures series, first one. Let me welcome Professor Joseph Prabhakar, who is going to conduct the class today, and also welcome Shritikanta and Ms. Bhagirathi, who will be looking for your questions and comments in the Facebook channel. So please, as I told last time, keep interacting with the lecture. So whatever points you want to ask, you can ask, and let it be a group discussion type of lecture. So with this introduction, let me also inform you that our Professor Satyanarayana, who is supposed to take, and he will be taking probably from the next week, I hope so. He is in Corona Care Center. He's all right, but he has been quarantined for some time, and he will hopefully take the next class or next class. So whichever way, but there will be a combination of the lecturers. Sometimes both of them will take, sometimes one of them will take. So the things will keep rolling now from now onwards. So now I will request Professor Joseph to start his lecture programs, and keep all of you listening and post your questions in the Facebook as well as in the Zoom, and you can always interrupt. Don't feel hesitation at all. It is not a normal classroom. It is a kind of a discussion. Thank you and welcome to this session. Professor Joseph Prabhakar.
Thank you, Venkatesan sir and Yogarajan sir. So as he mentioned, due to some unavoidable circumstance, Professor Satyanarayana not able to join today. So hope he will start his lecture from next week. So today I would like to initiate the discussion on classical mechanics. So as in the previous week we were discussing that it is going to be a rigorous course on classical mechanics, and the previous discussion, a lot of students shared their opinion that asking us to start from the basics. So it's the right time to first do some overview of Newtonian mechanics. Then we will start the analytical mechanics, or basically called Lagrangian mechanics or Hamiltonian mechanics, because it's not without understanding, appreciating the Newton's equation, there is no point of doing the Lagrangian mechanics or Hamiltonian mechanics. In fact, the Lagrangian or Hamiltonian mechanics, it's a updated version of Newtonian mechanics. It is not a separate mechanics or separate principles. Like we have in olden days, we have the big size mobile, right? 1100 mobile, Nokia or Motorola mobile. But now we have Android mobile, right? So what happened? The more technological improvement. So we have more sophisticated gadgets we have. So likewise, the Newtonian mechanics, it's a very basic model. Of course, it is also cover everything. At the same time, when you go for the Lagrangian mechanics or analytical mechanics, it's a kind of more sophisticated mathematical sense. We can the range of applicability is really vast compared to the Newton's equation. So that is the only advantage other than having the analytical mechanics. So mathematically, it's more rigor, more beautiful, there are various nice properties it owns compared to the Newtonian equation. So this discussion is based on this today class or today discussion mostly on the overview. We are going to see the overview of Newton's equation and related some important points. So as Dr. Venkatesan mentioned, if you have any clarifications, any questions, you are feel free to ask or express your opinion. I'll share the screen now.
Yogarajan, can you show his screen alone and also enable comments in FB?
Yes, those things already have been done. Already we have given permission for Professor to share his screen. Now he is sharing.
No, FB comments also.
Yes, already that was enabled.
But no.
It was already enabled.
Okay.
Otherwise,
So I hope
students, Professor, one minute. So supposing that if students are unable to give comments in Facebook, please give in Telegram. Okay, over to Professor.
So I hope the screen is visible, right?
Yes.
Yes, sir.
So somebody is writing in the screen.
Students are requested not to scribble. That was not disabled. So kindly, please don't move your mouse over the screen, please. Professor, now you may start.
Yeah. So my writing is clear, right?
Yeah, it is clear.
Yes.
So there are two parts in classical mechanics which we study in MSc. One is geometrical mechanics. Another one, analytical mechanics. So when I say geometrical mechanics, it's nothing but none other than Newton's So what I mean analytical mechanics, the Lagrangian, Hamiltonian or Hamiltonian Jacobi, whatever we are going to see. So why the Newtonian mechanics is basically called geometrical mechanics? I think most of you have already encountered. Whenever you try to analyze some problems, try to apply the Newton's equation, we need to worry about the geometrical configuration of the, for example, assume the particle moving in the inclined plane. So we need to use geometrical structure of vectors and resolve the vectors. So to apply the Newton's second law. Okay, so mostly the ideas other than Newton's equation is geometry. So that is the reason we always give a classification of geometrical nature. So when I say analytical, as you all aware of the content, like there is a Euler-Lagrange equation or Hamilton's equation of motion or Hamilton-Jacobi equation of motion. So those things are more analytical in nature. We may not even sometimes, of course, if you solve the problem in one dimension or two dimension, one particle, you can able to see and visually you can able to. But sometimes we have more than one particle, then this entire thing is solved in the configuration space. So there we may not have any visual perception, but we may have a lot of mathematical techniques that may not have any direct relation with the real space. So that's the reason it's more in analytical nature, and this is more in the geometrical nature.
Sir, excuse me,
So
sir.
here in this lecture,
Professor, one
Yes.
girl is asking a question. Yeah.
Sir, there is a comment in
Yes, ma'am.
Facebook that's can you speak louder?
oh, is it? Am I louder, Professor?
Yeah. Now
Ah,
it's okay. Sometime there was a disturbance. but otherwise fine. So you can keep
Oh.
somewhat a closer, the mic can be closer to you and then continue. I don't know whether it will hamper your writing. So, but anyway, it is
No, no,
audible.
but sometimes, yeah, actually, see, actually this happens.
That is because of the
two reasons.
network,
Either
not the mic. Network issue.
Yeah, network or maybe closeness of network.
But for me, it is okay. Professor.
So, okay, okay. So in this discussion, we concentrate on of course, in the previous discussion, lot of students asked about the principle of virtual work and the virtual displacement. Don't worry, most probably Professor Satyanarayana will join next session. He will explain thoroughly. So once we thoroughly understand the Newton's equation, the next part is the D'Alembert's principle and principle of virtual work and Lagrange equation. So that will be definitely taken care of. That just I want to add this because last session a lot of students are talking about that. Okay, so Newtonian mechanics. So what is the main content of Newtonian mechanics? Can somebody just open your mic and tell me what is the main content of Newtonian mechanics?
So Newton's laws, three laws.
So Newton's three laws. So the entire Newtonian mechanics codified in three laws. So the content will be laws of Newton. So what is the aim of Newton's equation? It is basically, it talks about motion. So how to quantify the motion, how to explain the motion, these are the two important agenda. So if you want to understand what is the reason for, what is the intention of having Newton's equation, the main agenda is here Newton's wants to quantify the motion and explain the motion. So now, even though it is basic, so please bear with me. I'll just a little bit talk about the three laws. So the first law, so can anybody say what is first law? Law of inertia, right? Just can you tell me what is the first law?
Every body continues in its state of rest of motion until it is acted by an external unbalanced force.
So external, okay. So somebody said, I'll write in. External unbalanced force. Right? So please understand, here she used a two word, external one, unbalanced one. In fact, there are, this is a common misconception about the first law. So make it very clear, the first law does not talk about the effect of force. Right? When you say unbalanced, remember, unbalanced means there are more than one force, right? Then what is the effect of unbalanced force? That is what it means. The first law talks about what is the nature of motion if there is no force. So this is a very important idea because the effect of force will be given in the second law. So first law talks about what is the nature of motion if there is no force. Remember, there is a difference between there is no force or there is no unbalanced force. So that is a point. So that's why I asked the students, because most of the students they talk about unbalanced force, net force. So that is a common idea they have. So first law, very important. It talks about
Sir, in FB, the screen
Nate.
is not very clear, sir. There's a comment in the FB that the screen is not very clear. Even for me, it's like that, sir.
is it?
No, what is not clear? Can you be louder, Bhagirathi?
Yes, sir. The screen, the board is not visible. One person is telling, sir.
But
It's-
are they seeing through mobile?
I'm not sure, sir.
Yeah, if it is a mobile screen, I think it may be very, very small letters and it is
No, actually,
clearly
no, sir.
visible.
Even if you see the mobile, you can able to see very clearly.
Yeah, you can see, but there is a lagging of communication to some people. So there was a comment saying that in my system, I'm able to see. So there is a possibility of network delay and disturbances. So I think let us see. Wait for some more time and let us see whether the problem persists.
Okay, sir.
So, very simply, I can say that if no force, so very in a more concrete way, if no force or no external force, then P is constant. That's what usually student in the school level we used to study that unless otherwise there is external force, the object try to continue state of motion, constant velocity or rest like that, right? So I want to just make it very simple. If remember, if no external force or if no force, P is equal to constant vector. I did not use the word if there is no unbalanced force. I will tell you why I did not use this unbalanced force. So what first law says, if I have no force, what is the nature of motion? So it says if no force, the particle has some kind of inherent property that's called momentum. Of course, that is the definition is mass into velocity. That inherent property cannot be changed on its own. It has to be constant. That inherent property cannot be altered by the object itself. So there is also another important point about first law. Remember, when I say P is equal to constant vector, what is the definition of P? Newton defines. What is the definition of P? This is nothing but very famous, well-known mass into velocity, right? But velocity is have a meaning only with respect to some reference frame, right? But we never, when you study Newton's equation in any textbook, they say only it maintain its state of motion. But with respect to what? With respect to what reference frame, right? Because the first law in itself involves the velocity. So when velocity has a meaning only with respect to some reference frame, right? Because velocity involves the position vector, rate of change of position vector. So then we need to talk with respect to some reference frame. So the first law, the question is with respect to what reference frame P is equal to constant when F is equal to 0. Remember this all with respect to what reference frame? P is equal to constant when F is equal to 0. So it says Newton's first law says, or that's what we call law of inertia. This is true only. The entire thing is true only with respect to inertial frame. So now I am suddenly introducing a concept called a word called inertial frame. So Newton's defined the content of Newton, the first law with respect to the inertial frame. Then we may ask, what is inertial frame? In fact, the concept of inertial frame and Newton's first law are inseparable with respect to each other. We can think of the inertial frame is defined through first law. I think this toolbox is really giving disturbance. How to hide the toolbox browser? Is it possible to hide?
Yes.
It's just a minute. Hello.
Tell me, professor.
Stuck ஆயிடுச்சு professor. ஒரே
ஒண்ணு இல்ல, ஸ்லோவா சரி பண்ணுங்க.
Keep on roll.
I think he as the number of 100 people are already there.
No,
One
I
of
am
us have to
really-
go
I-
out and then allow.
No, that also will not solve the problem because
Why?
they are in the waiting room. So that way
No,
you
no,
can.
let him in the waiting room. So you have to reserve. No, if you remove one by admission, only others can come.
Yes, I am removing actually. I am
You
removing.
remove one of us, maybe even myself.
No. You be there because two are now. I think he can enter.
Hmm.
Only 99.
Now you look for him and then
Yes,
allow.
I am looking for him.
Yeah,
Constantly.
okay. Right. So meanwhile, some students had asked some questions. How do we define the momentum? Other than P is equal to mv. I think some student has raised in the chat. Can you unmute and place your question?
Yes, sir. Hello.
You unmute.
Please tell me what is the question.
Sir, everybody defines momentum as just P is equal to mv. Other than
Ah,
that, what is that?
what is the different way of
Uh,
defining
yes,
momentum?
sir. Is it the rate of movement or something, or can we define like that?
Okay, very good. So can any other student here respond to his question?
Yeah. So, sir, can I
Yeah,
try?
yeah, please.
Uh,
Some student will be better, but anyway, still you can manage, you can tell.
Okay. So this is linear momentum is like amount of linear motion contained in the body. So when we say P equal to mv, it is just form of the momentum, but P equal to mv is not always. Suppose we uh, go to any other coordinate system, the form of the expression for momentum will change because v will be different. Suppose we are in uh, rotational frame, so v equal to omega are there, so form of the momentum will change. Okay, but so long as it is linear momentum, p equal to mv. This is basically the amount of linear motion contained in a body.
But even in a rotational frame, that is called linear momentum only, is it not?
It,
P dot omega
huh,
r.
that's what, sir.
That
P
is
equal
also a
to
linear. Suppose if you remove the force connecting the central point, then it will be simply going in a linear way.
p equal to mv. It is always there.
Yeah. So someone has said that you can we say that that momentum, we can call it as linear motion contained in a body, amount of linear motion in a body.
Yes, sir. That is
So,
Okay, Joseph Prabharan sir, we are just discussing something.
no, actually, எனக்கு தெரியல சடனா
It's all right, it's all right. It happens. It happens.
Okay.
Okay, just a moment before you go. Some discussion was there. How do we define a momentum other than conventional P equals mv? So some discussion was there, and Siddhikanta has given an answer. Depends. The expression may differ from frame to frame, but otherwise the literal definition, you can say what actually it means literally. Someone said that it is the amount of motion contained in a body. So in a different way, in a different perspective, can you define?
No, actually, this is the way to, yeah, as he said, the famous way to say it's the amount of motion contained in the, that's the correct way. So other, like for example, v is to omega cross r, all these things are, once you accept this definition, everything follows. So there is no other option for Newtons to quantify the or codify the motion. This is a thing that we can find even from Newton's Principia book. Maybe there must be some philosophical reason, but this is more mathematically it will work. Okay, I think I will proceed, right?
Yeah, please.
Sir, okay. Thank you, sir.
Okay, so remember, so I was talking about the real or the correct meaning of first law. So what I mean, so first law is the nature of motion when there is no force, because when we use the unbalanced, which means you are bringing two forces. There is a clear difference between no force and no unbalanced force. So now I said this momentum is constant vector with respect to a inertial frame. So how to define inertial frame the other way? Now, what is the definition of inertial frame? So what Newton says, whenever you are seeing some object and you are trying to see any forces acting on the object. If no forces acting on the object, and please observe the motion. If it has a constant momentum, then you are viewing or observing the particle or object with respect to inertial frame. So this is the way to define inertial frame. In fact, Newton's first law is basically definition of inertial frame. Otherwise, whenever you try to form some equations which involves the three-dimension, we need to refer with respect to some reference frame, right? So Newton's, before defining what is force, what is acceleration, he wants to define with respect to what kind of reference frame he wants to codify the equation of motion. So in fact, the first law says there exists some set of inertial reference frame. With respect to those reference frame, if object is not experiencing any force, its momentum remains constant. Is this clear to everyone? So we cannot separate first law and inertial frame. So this is an important point. Then now you can think of, is it possible to, somebody says that whenever you do in the for example, if I give you a simple example, suppose assume you are sitting in the train. Okay, so assume that you are inside the AC compartment. I hope those who are traveling in the AC compartment, you can easily recognize. In front of your seat, there will be a small tray where you can keep your bag or your laptop or your water bottle, something. Assume that you keep a water bottle on the tray and you are sitting. Assume the train is initially at rest. So what is the motion now? What is the nature of motion of the bottle? The velocity of the bottle is 0. And you find that, of course, there is a force in the vertical direction, but there is no force in the horizontal direction. Please understand, there is no force in the horizontal direction, and the vertical direction, there is no net force. I hope you understand the point. In the horizontal direction, there is no force. In the vertical direction, there is no net force. So we are not talking about in the vertical direction what happens. So we are now trying to see what happened in the horizontal direction. So now suddenly, if the train starts, because the driver would have sit in very, very long distance, you are sitting in the AC compartment, and you cannot see what happened outside. Suddenly the engine starts, what will happen? You see that the bottle comes backward. Suddenly the train starts accelerate forward, the water bottle suddenly falls backward. So now what do you think? There is no external force in the horizontal direction. How can it change its momentum? What is the initial momentum of the object? It's 0. Now you find that in horizontal direction, no force, but how can it change its direction? Is it a violation of first law? So in this case, whenever you see that without any external force, if the object change its state of motion or the momentum, which means you are not viewing or observing the object with respect to inertial frame. You are viewing the object with respect to non-inertial frame. So this is the way to reconcile. So there is no meaning of violation of first law, right? Whenever you see that there is a violation, which means you are not seeing with respect to non-inertial frame, you are seeing with respect to non-inertial frame. So this is an important certain point that we should understand about the first law.
Any questions?
So,
sir, that means first law defines inertial frame, isn't it?
yes, yes.
And now in the example, train
Because,
example,
see, that's
bottle is at rest.
Yes,
What is the inertial frame there?
Yes, see, if the train is at rest, or suppose if the train, assume that if a train is moving a constant velocity, you keep a bottle in the tray. What will happen? Whether a bottle will fall down front or back if the train moving constant velocity?
It will be in the same position.
Same position, it will
When
not
moving.
accelerate backward or forward, right? So
Yes,
which
sir.
means that now it's a perfectly the first law hold, which means what? The train is the inertial frame. You are observing the bottle with respect to inertial frame. Now assume that suddenly the train got accelerated by the driver. Right? Now what will happen to the bottle? Bottle, if suppose the train accelerate forward, bottle move backward. You see that bottle move backward. Suppose the train deaccelerated, the bottle try to move forward, right? So according to you, nobody is giving external force. Assume that the force given by the friction of the tray is it's a reference frame force, right? We are not going to consider the force given the reference frame because we are observing from the reference frame. So nobody is exerting force on the bottle, but bottle is either moving accelerate forward or backward because of the train acceleration, right? So it is not a violation of first law. What we are seeing is we are observing the motion with respect to non-inertial frame. So this is the very important subtle difference between the idea of first law and the inertial frame. So whenever, very simple, right? I want to tell in one line, whenever you see that no force acting on the object, please understand, I mean no force, not no net force. Whenever no force acting on the object in a particular direction, in this case, I mean x direction, then its state of motion remains constant, which means you are seeing the object or you are observing the object with respect to inertial frame. So what is the definition of inertial frame? This is the definition. Is it clear to everyone?
Yes, sir.
So now I want to go to second law. Remember what is first law? First law says if no force, what is the nature of motion? That's what I told, right? Now second law says if there is a force or net force, what is the nature of motion? So he wants to first define no force, what is the motion? Second law, if there is a force on the object, what is the motion? So he said he defines, remember this is also again, I mean after careful observations and experiments, he defines the force is equal to the rate of change of moment. Some people introduce is proportional rate of change of momentum and the constant is k. Of course, the k can be observed as when you try to define system of units, you can always define that the constant proportionality constant will be equal to 1. That doesn't matter. So he says the force can change the momentum of the object. So now we can easily understand the difference between the first law and second law. So the effect of force is to change the state of motion or the momentum of the object. Now we may ask the question, suppose if f is equal to 0, then what will happen? dp by dt is equal to 0. It implies p is equal to constant, right? This is what Newton's first law, right? P is equal to constant. Then why we are, which means is it a derivation of first law from second law? Is it a derivation of first law from second law? Can we able to derive first law from second law?
Already you have derived.
Yes.
No, sir.
Where I have derived?
P equals constant. There is
Sir,
no change
we
in
cannot
momentum.
derive the
Is
loss.
it a derivation?
Derivation. That's what you
Remember,
asked
is
now,
it
whether
a
you can
derivation
derive.
or-
Sir,
It
we
is not a
cannot derive.
derivation. It is a, yeah. So remember here, when I say P is equal to constant vector, I am defining, right? It is not derivation. I define that P is equal to constant. I am proposing, right? I am proposing the some kind of quantification. Second law says, I said again, Newton proposes that the force is related to the rate of change of momentum. Now my question is, if F is equal to 0, mathematically F is equal to 0, dp by dt is equal to 0, then P is equal to constant, which means I am able to get the first law. Then can we simply throw, if we are able to derive the first law from second law, then what is the need of having first law at all? Right? So remember, very important, it is not derivation of first law. So what Newton's second law says, if I have, as the one initially one girl pointed out, if no net force or no unbalanced force, then P is equal to constant. Remember, this I obtained from second law. This you cannot obtain from first law. So first law, it's only about motion without any force. Second law, if suppose if I have no net force, right, then automatically it says P is equal to constant. So very important, we cannot derive Newton's first law from second law. They are independent laws. So Newton's first law and second law are independent. And only thing is they consistent with each other, right? I'm giving two definition. They should not contradict with each other. At some case, suppose if I have some special case, like where if I have no unbalanced force, right, then automatically the conclusion given by first law, conclusion given by second law is same. That doesn't matter. Which means they are consistent. If they contradict, then they cannot have a two definition, right? So that's the point that I want to mention. Newton's first law, Newton's second law, they are separate definitions, are separate laws of motion. We cannot derive one from other. This is the important another lesson that you should get in mind. And very importantly, as I told you, again, the force is equal to rate of change of momentum, again, with respect to inertial frame. This is also true. Never happened this writing point.
Now, students have got any questions, you can place and discuss.
Just a minute, bro. My so Newton's second law is also valid in inertial field. We'll talk about how to modify the Newton's second law non-inertial. That is a separate case. Now we're not going to discuss about it. We'll discuss later. We have to include the fictitious force. So now I want to spend a little bit time on the second law itself. So F is equal to the rate of change of momentum. As I told you, it's mass into velocity, and we can have F is equal to m dv by dt plus vm v dm by dt. So we all know that dv by dt is nothing but F is equal to mass into acceleration plus v into dm by dt. So this is a very general form, but some cases, most of the case, what we deal with our UG curriculum or PG curriculum, most of the problem we deal with the constant mass motion. Suppose if mass is constant throughout the motion, then we'll have is the famous m into a or m is equal to dv by dt. So this is a very well-known school level thing. So what the second law says, either you can relate force is defined in terms of rate of change of momentum of the object, or we can always think of force is nothing but mass into acceleration of the object. Remember, force is a dynamical quantity and acceleration is the kinematical quantity that we are observing through some laboratory experiment. We can able to get or calculate or determine what is the acceleration by doing some experiment, right? So it says very important, the direction of force and direction of acceleration is same. Here, when I say reference direction of force, we can also include our net force and net acceleration. This is even though we take it as a granted, these are all important intuition given by Newton. Suppose if acceleration and force are different direction, we have completely chaotic. We may not have to do anything, right? We cannot proceed further. Fortunately, he formulated such a way that force and acceleration is the same on the direction. Now I want to ask you very important difference. What is the idea of Aristotle? Newton's idea of force will be F is equal to ma. What is the idea of what is the equation of motion given by Aristotle? he relates force is always directly proportional to velocity. But what Newton says, force is directly proportional to dv by dt. So according to Aristotle, if v is equal to 0, force will be 0. Is it true? Just think of, just now I told, if f is equal to 0, that doesn't mean that velocity of the object will be 0. I told you, if no force, the particle can be in the rest state or in the constant momentum state or constant velocity state. The particle can move even if I have no force. So this is a very, very important, the foundational difference between Aristotle's idea and Newton's or Galileo's idea. So in fact, they really, in fact, 1500 years, people believed that if no force, no motion. But now Galileo and Newton showed, even if I have no force, there can be a motion. There can be a constant motion. So what is the role of force now? It can only change the nature of motion. Either it can increase or decrease the quantity of motion. So this is an important difference. In fact, Newton really reduced the role of force. Aristotle says force is everything. Without force, nothing happened. Because his time is very, very different. The social structure is very completely different compared to Newton's time. So he said, yes, we can have motion, but to change the motion, we need force. So that is the very, very ideological difference between Newton's and Aristotle.
Sir, sorry to interrupt. When you write
Yes.
it down, no, we are not able to see because of the zoom at the last lines. So if you could stop before the when it is too down.
Okay, I'll sure. Thank you.
So what you have written there last, Aristotle not able to see.
Oh. No, what I want to try to convey, I have not written much. What I say that for new Aristotle says force is equal to, or force is proportional to velocity. If no force, no velocity, which means particle has to be at rest. If there is particle is moving, means automatically it experiencing some force. That's what Aristotle idea. But Newton says you can have a motion without even any force. So that is the main difference. Then another important one is the Newton's equation is the Newton's second law. Is a local equation. What is meant by local equation is f of t is equal to m p of t. So the acceleration experienced by the object at a time t is only affected by the or given by the force at a time t. So this is a very important. So that's why that is the meaning of local. If I have a integral equation, that's a global equation. So this is a instantaneous. The instantaneous acceleration.
Someone called Arun is scribbling. Kindly don't scribble. Don't move your mouse over this writing pad, please.
Sir, I have a doubt, sir.
Yes.
Sir, suppose if I am riding a car with a constant velocity, that means the acceleration is 0, right? So
yes.
Force is 0 means I didn't get it in that way.
Tell me again, I didn't get properly. Tell me again.
Means I am sitting on a car and riding with a constant velocity, sir. So my net means I am the acceleration is 0 when I ride.
Yes.
So my force is 0, but frankly speaking, how can a force be 0 while I am moving? Means I didn't understand.
No, see, there will be always a force, right? in the case of course, when you try to apply this kind of real world case, we have to be very careful. See, there is a tire is interacting with the earth surface. Otherwise, when you try to, there is no friction force and there is no normal force from the surface, the car cannot move forward. So what we can say, whenever the car is moving constant velocity, no unbalanced force. So that is a point. If there is no unbalanced, which means when a car is moving in a constant velocity, it has no unbalanced force. So that's the point. Because there is very complicated system like engine and it's having fuel. If you try to resolve the forces internally, it's really a complicated one. But in a whole say, you can say that when a car is moving constant velocity, there will be no unbalanced. I cannot say no force. There will be no unbalanced force. Is it clear?
I didn't understand means what is that unbalanced force, because the car is moving forward, right? So there is a position of the car is changing, so we are measuring the velocity. So when we measure that there is no change in velocity, so acceleration is 0. So means to the car to move, car to go moving, you need to what? Need to the oppose it. It should be greater than the frictional forces. So it has a net force. So only the car is moving forward. So there is a net force, and but acceleration is 0, right? So force is 0. So that's not it's not making sense. I am not understanding it.
No. See, the point is like initially assume the car is at rest.
Yes, sir.
Okay, agree, right? Now, what is the momentum of the car?
0.
0, right? Momentum of the car is 0 and car is at rest, which means now in horizontal direction, no force.
Yeah, vertical.
Okay. Now suddenly you want to change the momentum of the car from 0 to some non-zero value.
Okay.
Correct?
Yes, sir.
So for that, you need to give separately, you need to apply some force.
Yeah, yes,
in terms of right, you're applying some force not by your hand. In terms of the fuel is giving some torque to the engine. The engine is rotating the tire, and there will be some kind of, you are generating some force that will interact with the earth surface, right? The ground. All right. So now it is trying to push. So automatically the friction is coming to effect. There will be an unbalanced. Definitely, there will be a force in the forward direction. That's the reason it is changing from its momentum 0 to some non-zero momentum. Now the car starts to move.
Yes, sir.
Right?
Yes, sir.
Now, if the car starts to move, suddenly you stop your engine. What will happen? The friction force will come to rest the car, right?
Yes, sir.
Right? Now you keep on sustain. You keep on win the friction force. You need to constantly apply some force on against the friction force.
Yes, sir.
So if you exactly apply whatever the friction force acting on the tire, and the same force you are applying through the axle of the wheel, then whatever the momentum it gained just after the P is equal to 0, the same momentum it will continue. Right? You are keep on exerting force on the axle. That force is trying to overcome the friction force given by the surface. So totally there will be 0 in the horizontal direction. So it will keep on moving in the same constant momentum. Suppose you try to change the accelerator means, now what happened? Your force is really greater than the force given by the friction. So there will be acceleration. So it's a competition between the axle, the force through the axle and the friction.
Okay, sir.
In other words, if you observe an object which is in constant velocity, no change in momentum, does not necessarily mean there are no forces acting on it. Okay, so that is the inference. That like say, planets are moving, so many things are moving. It looks as if there are no forces. So it looks as if there are no forces, but it could be balances of the forces are 0. That is another thing. So that's how we can.
In fact, as rightly he raised the question. See how Aristotle concluded that if no force, no motion. So he thought that if I just throw the ball in the surface, in the ground, what will happen? After some time, it stops. Then what Aristotle thought, okay, since I have not, till I apply some force on through my hand, it is moving. Now I leave my hand, so object is left from my hand. It could not be able to move further forward distance. So after some time it stops because there is no force on the object. So that's the way he concluded. But what is really Newton said, once the ball leaves from the hand, you have no effect on the ball because you just import some velocity, ball leave from your hand, it is moving. But what happened? There is a frictional force acting on the ball. It is trying to reduce the velocity that you imparted on the ball. So finally, keep on reduces. Finally, at one moment, the friction force suck out all the velocity. It brings the particle to rest. Now, if you want to keep on sustaining the motion, as the friction is there, so you keep on apply some force, then only the particle can move at constant velocity. So if the constant velocity that you are getting.
Somebody wants
Yes.
to either reply or raise some comments. Some student was, can you please ask your question or your answer to the question, whatever.
Sir.
Somebody was interfering when you were talking as if they wanted to ask a question. You
Sir.
are free now to ask the question.
Yeah, someone called Pechiyamal. She intervened.
Kekala, you can ask the question if you want. There is somebody, Ebenezer also wants to raise some question. Please, without wasting time.
Good evening, sir. Am I audible, sir?
Yes, please.
So you talk about the inertial frame. You gave an example of train, right, sir?
Yes.
In the train, the acceleration is not zero. Am I right, sir?
No, the train is moving.
So the train is moving.
Whatever happened. See, if the train is moving at a constant velocity, assume, of course, please understand, I am now trying to looking at what happened to the bottle. I am not going to bother about, remember, I am not analyzing the motion of the train. I am in the case when I define when I try to define the inertial frame, I am analyzing only the motion of the bottle. I am not going to analyze the frame itself. When you talk about the train, then you are considering system. What is the system here? In your case, the train is a system.
Yes.
Then we need to analyze the train motion with respect to air. Then we have to say whether it is accelerating or moving on, whatever, completely different. My question is, or my definition is, if I keep a water bottle inside the train and completely closed, we cannot see what happened outside, right? We cannot have no information about whether the train started or we cannot have no information. Suddenly the bottle comes forward or backward, which means, of course, a priori that we can say the train started, but assume we have no information. Suddenly the bottle falls forward or backward without any external force from your perspective, which means the train, what you are seeing is observing from the non-inertial frame. That's what I want to say. It is not question of motion of the train.
It's about the bottle,
right? It's about Remember, whenever you try to analyze the Newton's equation, you have to first clarify what system you are talking about. You have to isolate the system, right?
Yes,
Here
sir.
I mean the only bottle, not the train itself.
Okay.
Train is a reference frame. The reference frame has lot of dynamics, lot of kinematics, it has whatever the chaotic thing. But what is the effect of that reference frame on the train? So whenever reference frame is exerting force, that we treat as a non-inertial nature.
Yes, sir.
Correct?
Yes, sir.
So in the case, remember here, the force given by the reference frame is not external force. We brought that as a non-inertial nature. Now the bottle experiencing the gravitational force, that is external force, right? So we should be very clear about what is external force. The force experienced by the object from the reference frame, that is taken graph as a non-inertial frame nature or non-inertial nature. That's the point. Is it clear?
Yes, sir. It's clear, sir. Sir, I also have a follow-up question, but it's about the normal force. Can we discuss it now, or should we go into later, sir? It's about the normal force.
What?
Normal
Normal force. Remember, normal force is also an external force.
Oh, is it just the opposite of gravitational force, or is it something different, sir?
No, it's a normal force is, see, the normal force arises
No,
because
I
of
think
the-
Ebenezer, you are again asking about non-inertial frame, is it?
Sir, no, sir. I'm asking about the normal force, sir. When we
Ah, yes.
usually when we usually draw the free body diagram, we
Yes.
say that when the gravitation is operating downwards, we consider upward as a normal force.
Normal
I'm
force.
asking-
That
I'm
normal
asking
is
that-
perpendicular. The meaning of that normal is perpendicular,
is perpendicular.
not natural or something. Yeah, okay.
Sir, that's a reactive force.
That's a reactive. No, actually, that is not a reactive.
Reaction.
Yeah, actually,
Reaction.
see, the point is, it's not. Yeah, as he said, it's a reactive force, not reaction force.
Oh, yes, sir.
See, because normal force and gravitational force acting on the same object, right? So that's very clear. So whenever when we talk about Newton's third law, the force action reaction will never act on the same object. Here, when you try to apply free body diagram, you are using the Newton's second law, not third law, right? Third law is completely different. I will come later.
So no.
So
Again,
perfectly, you can use the
let
mg
me
and n
put,
as-
Prabhakar sir, the normal force.
Yes,
the
yes,
normal.
sir.
The word normal is
Oh, that okay. The
equivalent
word is,
to perpendicular.
perpendicular surface.
To the surface. Yes.
Exactly in mathematical terms.
There is another meaning of the word which is used there. Okay. So I do not know whether that is confused. You may be already knowing it, but I'm just trying to tell that this is to be remembered.
Yeah.
When we say normal force, it is not something abnormal against abnormal or something.
Yeah.
Okay.
Another
Yeah.
important point is
One minute.
Yes,
Normal
sir, yes,
means
yes, bro.
normal means which is 90 degree to tangential. That is the exact mathematical thing. Normal is 90 degree quadrature to tangential thing. Right. If you draw tangent, normal will be 90 degree perpendicular to that tangent. So that is the way. Okay, professor.
So here, yeah, as he said, here the tangential means the tangent to the surface, right? So
Yes,
the
sir.
normal force need not always exactly opposite to the mg, because whenever the object is moving in the inclined plane, here the inclined plane object is moving, the normal force is perpendicular to the inclined plane and mg is different direction, right? So they need not be always opposite to each other. That is the part. Okay, so let us continue that. So the Newton's
Somebody
second law is
also asked
basically
one more
local.
question.
Yes,
That
sir.
what is exactly the meaning of local?
The
When you
local
say it is
means
local.
Instantaneous. It's an instantaneous equation. See, when we talk about some natural phenomena through differential equation, those mathematically we say the local description. Local means at a point what happened to the
Yes.
object, to at a point what is that. So it's only the acceleration of the object at a point at a time t is related to acceleration, the force given by the some external fellow on the object. So f of t is proportional to f.
Yeah. Another way to
Why?
understand is
Yes.
that so and so who asked the question, that when I say that you are a local person, that means your coordinates are limited to where you are. You are a local. So the same literal meaning holds good here. So here local means at a given time, at a given space. So that is the environment in which we have to understand the equation. So that is the local condition. At a given space and time, what value it holds or what a law acts on it. So that is the local. So here space-time is considered the place where the object is. Just like when I say you are a local of your village, so here again it is a local of that object with x, y, z coordinates of that particular place and for a particular time. So when the differential equation, you will also come across that dou by dou t or dou by dou x, which is a local derivative, which is in contrast to d by dt or d by dx, which accounts for all types of derivatives of the locality. So there are total and local derivatives. Here local refers to the x, y, z and t of that object, where it is. So the same property may not hold in another x, y, z and t sometimes, so long as that condition is not satisfied. So long as your locality is not your village. If you go to some other village, you are not local. So within your boundary of x, y, z, you can be called local. Same thing holds good for the object in question here. Thank you.
So I hope the word local means, I hope all of you get clear. It's only about the at a time. So why I am stressing this fact? Because when you try to solve this equation, the mechanics problem, people when you try to draw the free ball diagram, there's a common misconception. Suppose assume I am throwing an object very fast. Okay, the ball is moving. Then what is the forces acting on the object? Or what are the forces acting on the object? I am throwing the object very fast. The ball is now moving in the space.
Gravitational force.
What are the forces? Yes.
Gravitational force.
Frictional forces, sir.
So, pardon?
Yeah, frictional force.
Air drag.
I am throwing very fast. Is there any effect of
Air drag.
air drag force and gravitational force? Fine. What about my throwing? Do I have any effect?
So you're throwing the ball very fast. So you're transferring your energy, right?
I'm giving very large. Pardon?
You are transferring your energy to that ball, right?
I am also applying very large force, right? I am throwing
Impulse force,
I'm
sir.
giving larger force.
Impulse
Right.
force at a
Pardon?
shorter period of time.
No, I am just having the. I'm taking very slowly. I am gaining the large force. Right? I am applying some force, right? My question is now ball is in the air.
Contact force, sir.
So remember, whenever this is a very important subtle point, when the ball leaves from my hand, I have no effect on the acceleration of the object. So whether I am throwing very slowly, very fast, once the ball leaves from the hand, what I have done only to the ball, only I am importing either smaller velocity or larger velocity. Once the ball leaves from hand, the dynamics is taken care of by gravitational force and air friction. Suppose if you assume that no air friction, assume the air friction is very less, the entire dynamics is taken care of the gravitational force. My effect, whether I am throwing very fast or very slow, it's only up to till the ball leaves from hand. Once the ball leaves from my hand, I have no effect on the dynamics of the object. Then we can ask, what is effect? The effect is only I am giving different initial condition. If I throw very less, I am giving one kind of initial condition. If I throw very fast, I am giving another kind of initial, which means I am giving less velocity or more velocity. That's all. Once the ball leaves from hand, I have no effect. That's what the previous history has no effect on the acceleration, the present acceleration of the object. So this is a very important. That's what I said. Instantaneous acceleration of the object is referred to the instantaneous force. The previous history no effect on the present acceleration. Of course, the velocity has a previous history, but acceleration has no previous history. This is an important point. Then another important subtle point is related to the Einstein's relativity. I have F is equal to m dV by dt. Assume m is equal to 1 kg. Okay. Now I want to change the object. So assume initially the object the V1 is equal to maybe 1 meter per second. Now I am since I'm applying some force, definitely the velocity will get changed. So assume V2 will be 2 meter per second. Everything happens in del T is equal to maybe initial is 4 meter per second del T in a 2 seconds. Then what is the force? What is the force would have acted on the object?
1.5
1 kg into del V, V2 minus V1 is 3 by 2, right? 1.5 Newton. So what essentially I mean, I have an object mass is 1 kg. Now it has the initial velocity will be 1 meter per second. Now I want to change the velocity of the object from 1 meter second to 4 meter second. In a 2 second, we have 1 meter per second to 4 meter per second in the 2 second time. Then, which means essentially I need to apply 1.5 Newton. Now, let us try to have another example. I have the same mass m is equal to 1 kg. Now, the initial V1 is equal to 100 meter per second. And now I want to change from 100 to 104 in a 2 seconds. Then what is the force required? How much force required to change this?
2.
2 Newton.
Again?
Same.
Sorry, just a minute. 1 is it 3, right? It's 104 minus 101. Just a minute. Sorry, I think I have. It's a 101. It's 101 to 103. So from 101 to 103, I want to change from 101 to 103. Now tell me what is the force required?
1.5, same.
1.5, right? So even though it looks very simpler, it's very, very important difference. Remember, I have a mass which is moving from V1 to V2 from lower velocity here 1 meter per second to 4 meter per second. In a 2 second, I need only 1.5 Newton. Now I have the same mass, but it has a moving very, very higher velocity from initially it's 101 meter per second. Now I want to change from 101 to 104 in a 2 second. Again, I need 1.5 Newton. Is it true in all cases? Remember, when you go to relativity, special relativity, the force is in these 2 cases, right here, 1 to 4, here 101 to 104, I have only 2 same force. But if you go to relative higher velocity, this is not true. A very, very high velocity. Both cases, force required is same. But if V is very, very high, which means almost closer to C, then this is not true. What it implies, I have initially V1 is equal to 1 lakh meter per second, 1 lakh meter per second, and V2 will be 1.5 lakh meter per second. I want to change the V1 to V2 in a 2 seconds, right? The mass will be some 1 kg as it. So the force F1, I have some value. I have another case, V1 is equal to 1.5 lakh kilometer. See, again, it's 1.5 lakh meter 1.5 lakh meter per second, and V2 will be 2 lakh meter per second. Now, same 2 second, then F2, I have some value, they are not same. Please understand, this is a very important lesson. So Newton's first law, the Newton's second law is same when you deal with the change in momentum. The force required to change in momentum del V by del T is same in the lower velocity region. If you go to very, very high velocity domain, if you accelerate from 1 lakh kilometer per second to 1.5 lakh kilometer per second in a 2 second, the same mass, the amount of force is different than 1.5 to 2 in a 2 second. Even though the difference is same, 1 lakh to 1.5 or 1.5 to 2 lakh, the difference is same and time period is same. The amount of force that you want to apply is completely different. So F is equal to dP by dt. This again, this is a important inbuilt assumption. Remember, this is a F1 is equal to F2. Here F1 is equal to F2. In fact, it's a inbuilt assumption that the dV by dt is a small regime. The velocity, the absolute velocity is at the small regime. If you go to very, very high velocity, this may not be true. Is it clear to everyone?
Yes, sir. Special theory of relativity.
Yeah. In fact, if you want to express the Newton's second law, it will have some constant times velocity, some constant times acceleration. Both will have. Remember, we brought the idea of Aristotle. So the force is equal to some number times velocity, some number times acceleration. In Newton's mechanics, force is always proportional to acceleration, but in Einstein's relativity, force is not only proportional to the instantaneous acceleration, force is also proportional to the instantaneous velocity. This is a completely chaotic, non-linear way. Okay. So then another important point is the Newton's second law is a cause effect relation. F A. This is the important, of course, fundamental point. Now let us go to third law. So what is third law? Very simple. Everyone says action reaction will be equal, but I want to express in more mathematical sense. F12 is equal to minus F21. So if I have a object 1, I have another object 2. This is F21 and this will exactly F1. So notation will have to be clear. Some books follow. What I mean here, F21 means the first index represent the fellow who is experiencing force. The second index or second suffix represent the fellow who is giving the force. So F21 means the force exerted by the object 1 and the object 2. And F12 represent force exerted by object 2 on object 1. So it says the always equal and opposite. So F12 is equal to minus F21. And very importantly, action and reaction never act on. In fact, this is really law of nature. The third law is really law of nature. The first law and second law, even though we call it as a law, they are really a kind of definition, right? Because it talks about, it is not giving any definition. Newton says that always in the universe, whenever you try to identify some force, then automatically there will be always the pair, another force. There is no isolated force, there is no single force exists in the nature. So when I say action, reaction, very importantly, it is not cause and effect relation. Please understand, Newton's second law is a cause and effect, but Newton's third law is not a kind of cause and effect, right? So it's a kind of, it is not, it's a really a kind of law. There is no, you cannot say that this fellow is a cause, this fellow is a effect. They all act as a simultaneously. The action force and reaction force coexist. That's very important. So according to Newton's third law, there is no time lag. If there is a force, when you say that I am just giving some force on the wall, at the same instant, the wall is exerting force on me. They coexist. There is no time lag. Of course, when you go to the relativity, there is a issue that there is action at a distance, but we are discussing the Newton's regime. So it's a simultaneous no time lag. So this is a very, very important assumption. Sir, what is time? Can I?
So I think you can go for another some 10 minutes. Then we can have some interaction. That may be.
Okay.
This is the first session.
Okay. Okay.
Yes,
Okay.
yes, yes.
So now I want to conclude this, or maybe I want to summarize 3 laws. First law, what is the nature of motion if no force? Second law, what is the nature of motion if there is a force? And third law says, what is the nature of force? So first 2 laws talks about what is the nature of motion with force or without force, and third law talks about what is the nature of force. This is the content of Newton's dynamics. So if at all you want to summarize in 3 lines, this is the simple summary of the entire Newtonian mechanics. I hope, is it clear to everyone? And very importantly, I want to also point out this third law is applicable to only material particles, not human actions or human thought process. It's because usually whenever we find some media and some discussion, always says that according to equal action and reaction are same, so he beat me and I also want to beat him, or something like that. So don't apply Newton's third law to the life science. It is a law in the physical science, also applicable to the macroscopic object. Even if you try to apply to the quantum mechanics, it's not valid. If you try to apply in the relativity, again, it is also has some kind of issue. So it's very, very important. You should always very clear that it is only applicable to material particles, not for any psychological actions, humans' emotions. Okay. So now this is all about Newton's equation. What else there in the Newton's dynamics? There are very another important point, the conservation laws. So these are the 2 important building blocks of Newton. One is the 3 laws, the other one is the conservation principles. So what is the advantage of having conservation laws? it's one very simple advantage is even if the forces acting on unknown, still you can apply conservation. So if suppose I know what is the functional form of gravitational force, mg, or functional form of frictional force, I know mg. But what is the functional form of normal force or functional form of tension, T? I have no functional form. So whenever if there is a case, I have no explicit functional representation. In that case, it's really difficult to use Newton's equation. Those cases, we can easily apply conservation laws, either conservation of energy or conservation of momentum. For example, you take collision between two objects, right? Suppose if you want to try to analyze or solve the problems in the collision, we need to know what is the force acting on every time, every instant during the collision, after the collision, whatever. So exactly at the instant of collision, there is a force, right? This object is acting on force on this object, and this object is acting force on this object. That is a contact force. How to express that contact force? Is it possible to find some kind of functional representation? In fact, it is very difficult. But in that case, we can apply easily the conservation of momentum and get the solution, get the velocity, final velocity or initial velocity. So the conservation principle is a very important, powerful tool. It's not only in the Newtonian mechanics, it's also a very, very powerful tool in all modern physics. If we go to the particle physics, there the exact nature of force between the particle is really meaningless. We cannot have defined because it's everything is a pointless particle. So, but still we can apply conservation of momentum, conservation of angular momentum. So the conservation principle is not only important in Newtonian mechanics, it's also very, very important, has a very, very far-reaching consequence in other domains like quantum mechanics, particle physics, right? So, of course, later Satyanarayana sir will talk about that more detail, but I want to emphasize the conservation principle. So this is the one important point. Other, of course, conservation principle is also related to invariance or symmetry in the problem. Why we are interested? If we know some kind of symmetry or some kind of invariance nature in the problem, then we can able to relate to the conservation. We don't need to bother about what happened to the force. So conservation principle and invariance are directly related. I think I plan to solve some problem, but I think it's really, it will take some time. Maybe I will stop with this. If we have further questions, further discussion, we can initiate.
Yeah, I too request our students to unmute one by one, and they can raise their question. I think this part is very important. This is the first session. You have to deeply understand the fundamental principle. So without any hesitation, shyness due to language, don't hesitate. Please raise your question.
Yes, Dilly, I think Dilly raised the hand.
Sir.
Yes, Dilly.
Sir, if we take an object, I want to know what is the difference between momentum and the energy of object, either it's a potential or kinetic. if we say the momentum, it's also a quantity of object in a motion. But what is the kinetic energy, the formula or the term kinetic energy or potential energy says? And what is the difference between the momentum of the object or the energy of the object?
Yeah, it's it's a very fundamental.
Professor, if at all possible, kindly unshare your page so that we can see everybody's face.
Okay, fine.
Okay, Professor.
So very good question. Some students can answer instead of professor. Can any student throw some light?
Of course, it has no single answer. It's a very fundamental question. It has no single answer. Somebody can also.
And it is a literary meaning of the terms. If you understand, that may also help. So some other student can answer. How do we differentiate between momentum as a quantity from energy as a quantity? What do they make difference? Not the quantity in terms of number, but really what do they mean? Can we not say momentum in the place of energy also, or energy in the place of momentum also? How does that matter? So any other student, please?
Sir, I don't know if it is correct or wrong, but I'll just try. Sir, can I say?
Yes, please.
Sir, if momentum is nothing but if some mass is in motion, that will define as a momentum. If something is moving, it is in motion, something which possesses mass, that is momentum. Because it's just a definition, so we cannot go deeply into that. And energy is something that that object possesses, which can be what kinetic or potential. That is what I just think. I don't know if it is correct or wrong.
We also do not know many things whether we are correct or wrong. So don't worry. Anybody else?
I can answer just
Yeah,
an
please.
attempt.
Yes.
Momentum is something that momentum can be used as an interaction with the environment, and energy is something that the object which has it can only feel. So if in terms of interaction with the environment it's seen, then we consider momentum, and energy is in terms of how the body or the object possesses it reacts.
Sir, the basic difference is we can say momentum is a vector quantity, whereas the kinetic energy or potential energy is scalar.
Yes.
And second thing is we cannot measure the energy directly, sir. So like the momentum can be observed in lab. I mean, we can measure the momentum, and through momentum we can calculate the energy, sir.
Okay, so you are a bit quantitative in defining.
Yeah, what he said is correct.
No, let us not interfere. Some more students will answer. So just to give you some tips, say now our class is picking up momentum. Okay, and this particular student is energetic. What do we literally mean? We relate this literal meaning of the terms to our physics meaning of the terms without bringing out some vector, quantity, some of these things, because they have very close relation, the literal meaning and why they are used here also. Suppose a student is energetic. What do we mean by that? He or she can deliver certain things, no? I mean, so something in this connection, if you try to think, maybe it is a different way of looking at things. And we will come to know the real meaning of the terms used in physics also. That is what I feel in a different way. A person who does not know physics, if you ask him, you are very energetic, so what he feels? Why do we say that he is energetic? And then we say that now the vaccination program is picking up momentum. What do we feel by that? Do these two terms used in a literary way have any meaning in physics also? Can anybody tell some answers from this point of view? So there is silence. There is
Any other student?
There should.
So may I?
Yes, please.
So in that point of view, when we compare it with physics, I think that energy have a relation with physics, but momentum, I don't think that it have a relation with what we study in physics.
Okay, let us talk about energy. Since you connected both, please explain what it is.
Okay, so when we say a person is energetic, we say that he have an ability to do something more efficiently than someone else, which is
he has an ability to do something, first of all.
Oh yeah,
Efficiency, second point.
Yeah.
So he has some ability to do something. That something can be say work.
So
he has a ability to do work.
Yeah.
Okay.
So that we mean that he's more efficient than someone else.
That is he's a efficiently energetic person.
Sir, how fast he does, that is momentum.
Let us discuss about energy now. Is it am I communicating what you wanted to say?
Yes sir. Yes sir.
Okay. Do others agree with this? Professor may not agree, but do other students agree with this? That energy means an ability to do work in literal sense. Any other student agree or disagree or want to throw some more light?
Sir, I think momentum is related with motion, and energy is related with state of the mass.
State of the mass.
Or position.
Position of the mass. Okay.
Energy is
you are trying to think. That is correct. That is very important. Something related to the state, whether it is changing or stationary. In that sense, you are meaning? Probably. That's what I understand. It's state, whether it is in motion or in no motion, both are momentum is zero or it has some momentum.
Position, sir.
Position only. If position keeps changing, that is also one state. That is, it is in motion. Another thing is its position is at rest. That is another state. That means it is at rest. So I'm trying to think what exactly you are also thinking. So the state refers to its state of rest or state of motion. From that point of view, I'm just trying to extract some more from your thinking. Anybody else? Or Satish, am I trying to get you?
Yes, sir.
You can differ with me, no problem. Anybody else, please?
I think we are just comparing the common terms that common people use with the physics.
Exactly. Let us come from the common man's perspective.
Sir, it means some words are related, but some other like potential. We can say that he has potential. That doesn't mean that he has he's standing at a height or something like that. We cannot compare every term with the common term that people use, right? So
yeah. So sometimes the potential what the common man uses also seems to be related to energy. They may not be able to distinguish, but we use the terms in the strict sense of its meaning. That's what you want to communicate? Common man may not distinguish potential and energy. They may think, yeah, both are same. The person is having the potential to do. The person is having energy to do. Even he will distinguish. Common man also will distinguish. He will not use each term in a free way. But let us assume that he does not distinguish. But still he means something.
Yeah, yes, definitely. But
Okay, in that sense, momentum also he means something. So from there, can we get something to physics? So because when the science develops, it picks up the terms from literature, and it has a very clear grammar to pick up. Exact word it picks up. That is the difference between science and the common man.
sir, that means like you said, right? The energy is nothing but the ability to do work, right?
Yeah, yeah, okay.
Same way, we can say that momentum is nothing but how much fast you are doing the work. Means what is the pace at pace at which you are doing the work.
Okay. Suppose, okay. Okay, let me not further elaborate this. Any other student? Any other student? Please remember, this type of discussion will help you in an interviews. They will not ask you what is seen in the book or how you are writing on the board. They will sometimes try to understand whether you understood the term also. Anybody else? Okay, then let me give to professors or Sitikanta or one of you or both of you. Kindly clarify me whether I am right, or my friends in the group whether their sharing of the view is also right or wrong, or what is the right one.
Okay. So anyway, it's a nice discussion. What I feel, remember, whether it is in physics, whether it is a classical mechanics or quantum mechanics or whatever, there are certain fundamental quantities that we define. Then what happened? We mentally, before we define something, we are mentally able to process that. For example, assume the time t. What is the definition of time? Right? We cannot be able to define perfectly. But without the right definition, we are able to, our mind is trained to process. Right? So that is the way. Some in physics, whether we talk about energy, if you ask me to define what is energy, we cannot define. There is no definition of energy. But what we can be able to process, we can be able to, suppose if I talk about energy without understanding the meaning, but I am able to process, I am able to calculate. So this is whatever I am saying is from Feynman's idea, Feynman's explanation. Once he was asked to define energy, he said that we don't bother about whether we are able to define or not, but we are able to use it. Human mind is able to use those quantities without being bothering about the real definition. So this is the initial point that I want to mention. Now let me come to your question, the kinetic energy and momentum. Remember, if you accept that the definition of momentum P is equal to mv and F is equal to ma or dp by dt, then the half mv square is just some kind of scalar multiplication of this or some kind of modification of this momentum and first law and second law. Because he wants to, Einstein, the Newton wants to define the concept of work. Then automatically he found that if I move the object from this point to this point, he wants, remember, initially the object is at rest. Now I am applying some force, right? So the object is picking up some speed from this point to that point. So initially it is moving from in this corner to that corner. Then he apply his definition, right? His principles, first law and second law. He found that some quantity is changing from this point to that point. That quantity is not mv1 and mv1 to minus mv2. It is not momentum from this point to that point. He found that some kind of quantity is changing from this to that. That is nothing but half mv1 square half mv2 square. So that is a scalar number. So he gave a name that is a kinetic energy. So this is a way to understand. Philosophically, momentum and kinetic energy say, because if object has a more momentum, definitely has a more kinetic energy because p square by 2m. But how he defines, right? This half mv square follows from the Newton's first law and second law. So if you accept that p is equal to mv, then automatically Newton's wants to calculate some quantities. He wants to apply this two equations to the real world problem. He found that he needs to introduce some other bookkeeping device. This is kind of bookkeeping device from this to that. So what is changing? That is not momentum is changing. It's of course moment is changing, but really what exact quantity, the number, scalar number is changing is a funny way of combination of mv1 square of mv2 square. The change will be equal to the work done by the force by moving from one point to other point. So this is a kinetic energy assumption. Of course, why it is of mv square? It's follow from the second law, and there is another important deep meaning. Since our space is isotropic, so definitely that v square, because v square does not bother about whether it is a minus v or plus v. Space has a inbuilt isotropicness and translation invariance. So automatically that v square, there is no v cube or there is no v power v. It's a v square, the first even power. So I can say that it is follow from the Newton's law, and also it is a fundamental property of the space. So this is my point. Of course, you can also the Siddhikanta also can share his opinion and point of view.
Yes, sir. Same what sir says, that momentum conservation is a very fundamental thing of isotropy and homogeneity of space. That means at one part of space is similar to other part of space. This translational invariance lead to momentum conservation. This is what sir said. I to say this. Yes, sir. Sir?
Hi.
I was audible, sir.
Okay.
Yes,
Okay,
yes,
okay.
Yes, sir. Sir, one more point what sir was saying, I want to add that in the discussion, sir was saying no two philosophy of this Aristotle and Galileo. Aristotle thing he was thinking, sir told that he was thinking force is something which is required to maintain the motion. But Galilean thing is force is not something which is required to maintain the motion, but it is something to alter the motion.
Yeah.
So these are two viewpoints. Like someone is asking if somebody moves in a car with uniform velocity, and if he does not look outside, then he cannot feel that whether he's moving or he is at rest. So that means there is no force on it. But whenever he changes the direction or he moves faster or slower, then he feels that okay, he is moving. That is because he feels a force. So force is something which is required to alter the motion, not is required to maintain the motion. This is what I want to
say. I think somebody said that there is a question comes from the chart. I'll just look at. Yes, as I agree with the Siddhikanta, what he said is correct, of course. There is, sorry, in the case of black hole, the Newton's third law does not seem to hold, right? Of course, why you are going black hole? Black hole, see, if you go to very closer to star, of course, Newton's dynamics is completely ceases. We have to talk about Einstein's general theory of relativity, especially if we go to black hole, inside the black hole, up to a certain extent, we can apply general theory, but exactly at the singularity, no laws of physics holds true, because we don't know what happened, what is the nature of singularity. That's what the last year Nobel Prize given to the Roger Penrose. He proved that in singular, up to singularity we can able, but at singularity we cannot have any laws of physics. Known laws of physics is ceased to valid. So definitely Newton's third law will not valid. Not only black hole, even it is not also valid in the high velocity. If you try to use special relativity, Newton's third law will not hold, because Newton's third law talks about action reaction at the same time, instantaneously. But what Einstein says, any signal can travel only at the velocity of light. You cannot travel at instantaneous time, right? So this is a very important one. Like for example, if you take a Earth and Sun, suppose suddenly Sun stop its gravitational force, which means it suddenly disappear. then according to Newton's third law, immediately the earth will not feel the force. The signal is traveling instantaneously with the, but Einstein says, no, it takes some time, 8 minutes, 20 seconds. So information cannot travel greater than velocity of light. So in that case itself, the Newton's third law will not hold.
Anyway, let us understand the forces on earth better. And these are informative knowledges. And Professor, shall we conclude?
Yes, yeah, anybody have no other question? Of course, any
if
Facebook
anyone,
questions?
Students has, they still, I think students may have some questions.
Yeah.
No, because we'll have to, no, next session also they can come with the questions.
Okay.
And some questions they can continuously discuss in the Telegram group also. And any other questions in the chat, FB chat?
That Bhagirathi?
Oh, sir.
No, but often I saw the comments that FB chat is disabled. So Yogarajan, please let us see how it is happening.
That I have to check, I think.
Yeah. Okay. Students, come with more questions. Also, this is just an introduction session. As we go, you will be dealing with the analytical mechanics, what Professor has indicated in a more slightly rigorous way, so that we can enter into the subjects. Any point, Professor, now to say?
No, I think it's fine.
Okay. Siddhikanta, any points?
No, sir. It was nice. I want to say the discussion was nice.
Okay.
Sir, give the discussion very nicely.
So, yeah.
In fact, we can also see there are a lot of things, even the same Newtonian mechanics, there are a lot of subtle points are there, even in the laws of conservation of momentum, how the conservation of momentum arises, from where, as Sridhar mentioned, there is a symmetry, and that also can be dealt with. So maybe later, if we have time, then that time we can also discuss those things in the same, in the Newtonian mechanics itself.
Yeah. Okay, so this is just an introduction, and next session we'll have a bit systematic discussion on the, I think so, on the Hamiltonian and Lagrangian mechanics or Jacobian mechanics. So with this, let us wind up today. It is already time nearing 10. And please discuss in the Telegram group also. Keep exchanging among yourself. And we will meet next week.
Only one more question I want to post, maybe the student can think of when they come next session. I told Newton's first law, Newton's second law are true in inertial frame. What about Newton's third law? Is it true in initial frame? Is it hold for non-inertial frame? So this is an open question I posted. So you can just think of on next session.
So its reaction we will see in the next week.
Yes.
Okay, friends.
Yeah.
Yogarajan, any point?
I have no point. So if everything is over, then I have to stop streaming and close the session.
You can stop streaming. Thank you very much. Good night.
Good night to all. Thank you.
Really had a fantastic session, Professor.
Thank you, sir.
Okay.